Hi. So, look, we are actually very close to finishing our description of the production side, production structure of the economy we are building. So, now let's see if we can actually say something about demand for labor and demand for capital from what we have already established. And what we've established is that in equilibrium, this is the optimal ratio of capital to labor. And look, quite easily, out of this, I can calculate what is the labor in, maybe let's start with capital. What is the capital in equilibrium? Because we get Km, all we just need to do is to multiply both sides by Ln. We get alpha m over 1 minus alpha m W over R times Ln. Right? Now, I could do the same thing for labor, a little bit more complications, because now I would have to put this on the other hand side. So I would have that Ln is equal to, we would definitely have Km at the end, but now we need to divide it out, right? Now I would have to divide W multiplied by R. And of course the same here. Okay, but of course we're going to use the first result to devise demand for labor in our economy. Look, what we need to do, like, let's still assume we want to produce 1 unit of manufacturers. So we get the production function is Km to the power of alpha m times Lm to the power of 1 minus alpha m. So look, now that I know the optimal amounts, I can just substitute them back into the equation. But of course we will do it one at a time. So I'm going to substitute labor, I substitute this expression for capital used in the production of merchandise. And look, out of this, right away, I'm going to get something like that. Alright? But I can use what I've got over here. And look, here's Ln to the power 1 minus to the power alpha m times labor to the power 1 minus alpha m. So those two so I can, okay, maybe I'll write it differently, because now, right, you can see that those two will cancel each other out, and I'm going to just be left with Lm. So look, I'm getting that Lm times alpha m 1 over minus alpha m W R to the power alpha m is our production function where we already implemented equilibrium capital, and what we want is to produce 1 unit. And look, let's focus our attention just on this part. Look, I can easily solve this for capital. I just need to divide both sides. For labor, I'm sorry, just need to divide both sides by this. So I get that Ln is equal to alpha m 1 over alpha m w r to the power negative alpha m. Okay, look, what I want to do is to represent labor as a function of wage and rent. So I'm going to be assuming that wage and rent are the only two things that can change over here. So we're assuming that capital intensity parameter is constant. And what we actually got over here, this is demand for labor. Please, at home, do the very same thing for the, with the demand for capital. The only thing you need to change is that instead of putting this here, you will put this over here. Of course, the results are very similar, but do it as a form of practice. Now, if this is the formula for labor, maybe we can get the shape of labor, and what happens to the labor demand? We can get the shape of labor demand, and what happens to labor demand as rent is changing? Well, the easiest way to do this, of course, is by calculating comparative static derivatives. So let's do so. First, we want to draw the shape of demand function. So we need to calculate first and second partial derivative of Ln with respect to wage. So, okay, and here, first, if we wanna differentiate this, we need to use the chain rule. So first, this coefficient, the derivative of a function outside, this coefficient goes outside, and then we've got a derivative of the function inside, right? Derivative of the function inside will be alpha m, 1 minus alpha m, times 1 over r, right? This is derivative with respect to w to the function inside. And then we just rewrite the same function and we subtract 1 over here. So, alpha m, 1 over minus m, w over r to the power minus alpha m minus 1. Now, positive or negative? Well, this expression is positive, clearly, right? Positive, 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 positive. We take it to some power, we're going to still get positive number. Then, everything here is positive as well, but we have minus in front of capital intensity coefficient, so it needs to be lower than 0. And it makes sense. The higher the price, the lower the quantity. This is the law of demand. But let's get more details about the shape by calculating second derivative. Okay, so I need to differentiate this function now with respect to w. And I need to do it in the same way. First, this part goes in front. So get negative m times. Then we will have this part, because we treated this coefficient, plus it's also a derivative of function inside, so we will have it twice. And finally, the same expression we had at the very beginning, but now to the power negative alpha m minus 2. Now, is this positive or negative? Well, still positive, taken to some power positive. Positive number is this in total is positive, we get that here the second derivative is positive. What does it mean for us? Well, the function we are dealing with is clearly concave. So, how will it look? I'm sorry, convex. Convex, of course, convex. Convex, because second derivative is positive. Okay, so here we have labor. Here we have wage. So, this is a downward sloping convex function. So, first we clearly derived demand for labor in this economy, but what will happen if rent goes up? Okay, this we can also establish using partial derivatives. Okay, and now we unfortunately gonna have a little bit less nice thing to calculate, but it's still doable. Okay, first, chain rule, this part goes up front, and we now calculate derivative of the function inside. Remember that here is r to the power -1 plus the coefficient. So this part will stay the same. And now r to the power of -1, we will get negative r to the power -2. So we will have r squared, and minus up front turns into a plus. And finally, we will write the same expression. And we subtract 1 from the power. And we already know that this is positive, this is positive, positive, positive. So look, we see what happens if rent goes up. Now look, so this shows us that if rent for some reason increases, demand for labor increases as well. Okay, how can we how can we explain this? Well, it's pretty easy, and we've seen this many times, even in the previous video. If rent goes up, capital becomes relatively more expensive. So what the company should do? They should start substituting capital with labor. But when they do, it automatically means that the the demand for labor must go up. Okay, now what I really would like you to do is to do the same thing for capital. And look, actually you will get exactly the same result. But make sure that you can get there first by manipulating the production function, then by calculating all appropriate comparative static derivatives. Now that we know how demand for labor looks like, and we can say that the same thing will be with capital, because if I would change capital here, rent here, and W here, this would be demand for capital, right? So, how does the changes in wage rate or rental rate influence the equilibrium obtained by the producer, so that minimizing cost capital to labor ratio? Well, we can see this graphically. Okay. So let's start to some ISO cost. Let's call it I1, and this will be M1, because we are still interested in producing just one unit of manufacturers. Okay, so what we've got over here is optimal level of labor given wage 0, we'll just say W0 and rental rate, and the same goes with and over here we've got some optimal level of capital given wage W0 and rental rate. Now look, what we want to see now is what would happen if wage would go down. So wage is going down. Okay, how will we see it in the graph? First thing we would see is that, look, this point is showing us how much labor we could purchase at most, right? So if we would just purchasing labor instead of capital, we would be purchasing this much. We get it, so now, what if wage is going down? It means that this point must move somewhere here. Why? Because now we can afford to purchase services of more labor with the same money, right? So our isoclus line is changing the slope. And remember, the slope of isoclus line is negative W over I, right? So look, if wage is going down, it means that this function is getting flatter, right? Because it's becoming less negative. So we would obtain isoclus line like this. Okay, let's say that this is let's denote it like this. Let's make it into a dashed line. And now, is this it? Should we use this or maybe this one? Well, the question, if the problem is if we can produce at these points, of course we can. It's not a problem. It's on our ice cost line, but is it the best option? Look, we can clearly see that we can produce the same amount using less of both factors of production, so minimizing the cost. So again, we need to move this line over here until we find a point at which this line is tangent to the just one place on the iso point. And look, as a result, we obtain new optimal level of labor associated with wage W1 R and a level of capital K1 associated with wage W1. So what has happened? Actually, look, in this case, when wage went down, we are still producing the same amount, just one unit of manufacturers, but now we will be using more labor-intensive technology. Again, remember, this is a long-run result. This is what will happen over a long period of time. When companies have enough time to adjust to sell off some capital or just let it depreciate and instead hire more people. Look, in the example you can think about it is if you have a company that hires only local workers, but then the country where this company is located opened up the borders, and there comes a lot of immigrants offering to work for less, right? Willing to work for less. Generally, if we have more workers on the market, this should drive down the wage. And look, of course, the company is not able to just, take and sell all the capital, hire more people. It requires time. But this is what we talk about. This is a long-term result. When now, for the company, more labor-intensive technology is just better. It gives it optimum. And look, of course, we could obtain the same result in the opposite direction. If rental rate would be going down, we would expect for this ratio to become lower, and become bigger because we divide by a smaller number. So this function would be becoming steeper, and now we would be more. It would be more attractive to use even more capital-intensive technology. This is a situation where, for example, government introduces minimum wage that is very, very high. Of course, at the beginning, companies cannot do much, but how will they adjust? Now, for them, it is going to be better to purchase more equipment, purchase more advanced machines, and lay off some workers. This will be the optimal choice. Okay, and I think this is it about the factors of production that we need to know right now. The only thing we haven't discussed much is constant returns to scale, right? We already implemented them in the production function. We haven't discussed what it actually means for our model. Okay, but let's start with the beginning, from the beginning. So we've got constant returns to scale. Okay, now, in our case, this means that if I'm going to say A capital and I'm going to have A labor, then how much production will I get? Look, our production function is given, of course, by M equals Km alpha M times L1 minus alpha M. What does it mean? Look, now if I would double level of capital, double level of labor, what would I get? Look, I can multiply it by any number, and what am I getting? Look, out of this I get A to the power alpha M, but out of here I'm going to get A to the power 1 minus alpha M times Km alpha M times Lm to the power 1 minus alpha M. So we see that those two cancel each other out and get just A. And now this is equal to M. So look, constant returns to scale imply that if I double the level of labor in a company, I should double double a level of capital, I should double the level of production. Okay, pretty simple, we've done it in a lot of classes. What does this imply for our model? Actually, this assumption is the key to solving lot of problems. Normally we would encounter. Okay, let me show you this on the graph. I already need to warn you that the graph is not going to be perfect because I'm not a robot, but I'm going to explain what should be parallel to what. Okay, so we've got labor here, we have capital here. Okay, this is our isoquant. Okay, and let's just say, okay, and this is our level. This is how we produce 1 unit of merchandise. Now, so I have here so L, I have some K, and I got some point A. So in order to produce 1 unit of merchandise, of manufacturers, I should use this much labor and this much capital. So now look, what would happen if I would like to produce 2 units of merchandise of manufacturers? Well, probably, well, not probably, but definitely, in the context of constant returns to scale, I should double the labor and double the capital. And actually, look, this is what we would do here. Look, it turns out that we need to use just twice as much labor and twice as much capital. And we will be able to produce 2 units. Oh my god, I'm already seeing that this line is not gonna look the way it should. But unfortunately, like I told you, this is another one. Now, what if I would like to produce 3 units? If I want to produce 3 units, I would get to use 3 times as much labor and 3 times as much capital. Okay. Now, as it turns out, look, in this scenario, we observe some very special characteristics of this assumption that are very convenient for us. Look, first of all, you see that actually, if I know what is the optimal production strategy to produce 1 unit of manufacturers, I will know optimal labor to capital to labor ratio to produce 2, 3, and n units of manufacturers. So, what should be here is that if I would draw a line that goes from the origin here, it would be cutting through all those optimas for 1 unit, 2 units, 3 units, 4 units, and it would be cutting through every optimal point. Now, what is the slope of this line? Well, we already discussed this. It's alpha m over alpha m over 1 minus alpha m w over r. Right? Now, what is the slope of these lines? Well, again, look, if we will get the same optimal condition, right? So the slope of the isoquant and the slope of this line of isocost must be the same, and they are. So look, what is important to remember is that all those angles, let's call them gamma, are the same. So look, all those isocosts are actually parallel to one another. They just represent bigger total cost associated with the bigger level of production. But we already established the best technology, and by best technology we mean best capital to labor ratio. No, not best technology, I'm sorry, technology is given. The best capital to labor ratio within a given technology. So we actually we use technology that is to some extent capital and labor intensive, but look, once we are able to find the first point, we can just multiply and we are able to find any point. And this actually closes down our production structure. Look, I know that it wasn't a very easy and pleasant way to get there, but look what we've learned. We actually created entire production structure of the economy. We have two factors of production, two goods. Now, we were able to obtain optimal capital to labor ratio for our economy and associated costs with this optimal labor ratio. And now look, if we are able to do it for one company and producing one unit of good, thanks to the properties associated with constant returns to scale, we can extend it to as many units and as many companies as we want. And this will close the first part of our model. Next time we are going to introduce a little bit more about factor prices. Okay, thank you and see you in the next video.